Hey guys, it's Engineer Liu here. I know it's been a while since I posted some video here, but here I am. I'd like to present to you a software I made, programmed in C language, which is my own Navier-Stokes solver. Let me show you a quick example of what it can do. Here is the cavity flow, the two-dimensional cavity flow for Reynolds number equal to 1000. It is based on finite difference, explicit finite difference schemes from second, fourth, and up to sixth order finite difference schemes, and time advancement in the time advanced is Euler. It's a simple Euler scheme. Okay, so I made this solver from scratch using C language because C is fast, and I wanted to challenge myself. And also, I'm working right now with C, so I thought myself, why not program in full Navier-Stokes library solution in C language. So I posted this code on GitHub. You can check for github.com/araujo88/CNavier. So I didn't write any code documentation yet, but I'm going to. I'm working on it. It will be a very extensive, very lengthy documentation, since it has many libraries. So it includes linear algebra library, matrix manipulation, all this written from scratch. Also a Poisson equation solver, which we'll get on further on this video. So basically, this directory here is the main repository directory. It has, let me make some, I need to do a make clean here. Okay. Right. So we have the source folder as RC, which is the basic structure for a C project, a source, and an include, where we have the header files. The first library I wrote, which contains you could say the core of the solver, is the linear algebra library, which deals with matrix manipulation. So I created a struct called matrix, which stores a double pointer which contains the matrix itself, the number of rows and the number of columns. A vector structure, which contains the pointer to the vector and the number of elements. So this variable here I didn't utilize in this code, but I maybe will be utilizing in the future, but nevertheless it's here already implemented. So here we have some functions which I implemented and utilize for matrix manipulation. Here's a function which takes, for example, an argument and a matrix as an argument and sets all its elements to 0. Here we have the memory allocation functions here to allocate memory to the matrix. Here to free the memory. In C you have to free the memory, otherwise you have memory leaks, which could potentially freeze your computer. Something that happened to me while writing this, because there was some pointers I forgot to free, but we'll get to that in further. Here is a function which I don't utilize yet on this code. I tend to implement more functionalities, which is basically it's a function to read a matrix from a text file. So you could, for example, start a flow simulation from a given flow field. So you could read a file name here, and then it will allocate memory to a matrix and sets its number of rows and number of columns. Here's a basic function to print matrix function. Here's a function for the similar set of functions for vectors. Here it's a function for matrix multiplication, for Gaussian elimination to solve a linear systems, which we'll be needing when I develop further this solver, this code. Here's the Kronecker product for two matrix. It returns another matrix as a variable. Here is a reshape function which I will be utilized a lot in this code to change the dimensions of a matrix. For example, if you have a matrix which is 3 by 3, you can reshape this matrix into a matrix which is 9 by 1, transform into a column vector to perform some mathematical operations. Here is the function to generate the identity matrix, which is a matrix which have a diagonal filled with ones. Now all of its other members are zeros. Here is a function to allocate memory and initialize a matrix with zeros. It does both things and return matrix structure, type def variable that I created here. And well, we have a function to return the max element, to change the sign of its elements, and the minimum element, and a function to copy a matrix B into a matrix A. Right, so this is at the moment the linear algebra library that I wrote for this Navier-Stokes solver. And perhaps in the future I will be implementing more stuff here as I'm going to be needing. Of course, all the variables are double since we are dealing with large floating point numbers. Okay, so let's check. Okay, we have this finite difference library, which basically we have two functions. One computes the finite difference matrices for the first derivative, and the other one computes finite difference matrices for the second derivative. You have to inform the size of the matrix you want to generate, the order, which is second, fourth, and up to sixth order, and of course the spatial, this length of your cell discretization. The other library, let's see, we have the Poisson solver. Here I defined this constant pi, but I didn't end up utilizing it, but it's a Poisson solver, which I would get into more detail next. And well, we have a fluid dynamics library, which computes the Euler time advancement, computes the continuity equation to check if the solution is converging, computes vorticity based on the derivatives of velocity dv dx and du dy, and it will be implemented a function to compute the pressure, but for the present moment, I didn't. It's not yet implemented. Okay. Next, we have the utilities library, which here I will use in the future for isotropic, homogeneous isotropic turbulence for generating random numbers, like in this case a white noise, for example. And here is a function to print the VTK with header files, including the matrix for data visualization in ParaView, which is this software here in case you are not familiar. Okay, so I used ParaView to visualize the data. Okay, so this is an overview of the libraries. Let me save this right here. So here we have the main function. For the present moment, it doesn't take any command line arguments argv, but I'm going to add it perhaps in the future. There's a lot of things that can be improved on this code, but I decided to release it right now because it is ready to perform some simulations. So basically, it has a lot of inputs. The Reynolds number. In this case, we are limiting this to incompressible flows, and all variables are dimensionless. So it almost you must make dimension analysis of the flow you're going to simulate and discover which is your Reynolds number, right? So here is the length in the x direction, the length in the y direction, or the width, whatever. Here they all set to 1 because for the Reynolds number to make sense, I mean, we have to set the domain length in the x and y direction to 1. Here are the number of points in the x and y direction, also inputs, the time step, the final time of simulation, which is also everything is dimensionless. Here the max Coulomb number, which if it checks if your numerical parameters are, if they will not lead to unstable solution. Here is the order of the discretization for the finite difference matrices. Of course, the spatial derivatives. So I set this to 6th order. Here are the maximum number of iterations for the Poisson equation, which I will show further. Here set to 10,000 iterations. And convergence criterion for the Poisson equation, which is 10 to the minus 9. Here are the boundary conditions. We have the internal field, which is initialized with zeros. The fluid is at rest. So here we have the boundary conditions for the x velocity u and the y velocity v. So this is all set to 0, and here we have the top boundary condition of the cavity flows set to 1. Let me check for documentation. I have something here. Python. I was doing also a version of this in Python. String py. Here it is. So the documentation will be something like this. Okay, so this will be another solver I'm working on, but written in Python, since it is more user-friendly and easier to deal. We don't have to worry about pointers and stuff. So here it's an overview and methodology, governing equations, the continuity equation, the Navier-Stokes equation. We have the formulation used on this solver, which is the stream function vorticity formulation. So basically, you take the Navier-Stokes equation here, which is already dimensionless, and you take the curve for both sides, and then you obtain the vorticity equation. So since the solver is two-dimensional, we have this term here vanishes, and since the flow is incompressible, this term here also vanishes. So what we are left is this equation right here, which is a lot simpler than this equation. So here's the vorticity in a two-dimensional flow, and we also have to compute the stream function, which is defined by this Greek letter here. So we have the stream function equation. Here's how we can construct a stream function from the velocity field. So we have a closed problem for equations and for variables. So first we compute the boundary conditions for velocity, the initial conditions, and then we can make the time advancement through the vorticity equation, which is this one here. And then we need to solve a Poisson equation, which is this equation that relates the vorticity to the stream function. So this is a Poisson equation that needs to be solved, and I will show you in the other module I wrote for the Poisson equation. And then we can obtain, through the derivatives of the stream function, reconstruct the velocity field as shown here, right? So of course we can reconstruct the pressure as well, solving another Poisson equation. In Cartesian coordinates, we arrive at this equation here, which I will be implementing in the future. Okay, so we have the numerical methods here discussed, second order explicit center of a difference scheme. We arrive at these operators here, these derivative operators, which are essentially matrices. Then we can make the time advance as shown here. Here's the Kronecker product I talked about. Here is the identity matrix. So you can see why I had to implement the Kronecker product and the identity matrix in this code. So here is the discretization for the derivatives. Here's central, forward and backward scheme. So we arrive at this matrix here for, this is the second order finite difference matrix for the first derivative, has these coefficients here. This is generated on this library here. Here's for the first derivative. So if the order is set to 2, then it initialize and allocates memory for this matrix D here, which will be the derivative operator, and then sets up the coefficients and then returns. If it's fourth, it sets the coefficients and so on, and also for the second derivative. Okay, so the time integration, here's the F operator, which contains all the spatial derivatives. So on this code in the Python, I have implemented these other time advancement schemes, but on this code I implemented the Euler explicit Euler scheme, which is very simple, straightforward to implement, as I will be showing you. So here's fourth order Hunji-Kutta scheme, which is very popular. And here I talk about the fast Poisson solver, which use the fast Fourier transform, which I don't utilize on this code. Here's the stability criteria given by the Cohen number and the SFL, Cohen-Friedrich-Lewis condition, convergence criterion, and algorithm solution, which I didn't finish writing. Okay, so I hope that despite being incomplete, this guide could give you a good overview of what the code is doing. So back to the main function. Here I compute the cell sizes based on the inputs. Basically the inputs end here. Okay, so this is our standard auxiliary variables. The inputs of the simulation are these ones right here, including, of course, the boundary and initial conditions. So in the main function, it proceeds computing the cell sizes in the x and y direction, generate the derivatives matrices, computes the identity matrix, and computes finally the derivative operators, which are these matrices here, by the Kronecker product, right? So since I don't use, since these matrices here are no longer utilized, I free the memory, so to avoid memory leaks, which I had a lot. I already said that, but I really did, and I will show you how I managed to avoid that. Another input that you have to give to the program is the output interval of the VTK files that will be utilized for flow visualization. On this case, at each 10 iterations, the program outputs a VTK file with a field to be specified. Here it checks for the stability criteria with the two Courant numbers. Okay, so now here the variables are initialized, x velocity, y velocity, vorticity, string function, the derivatives, all the derivatives that are used. Here is a matrix that checks the continuity equation in all the flow field. Here are some auxiliary variables, which are all matrices type of variable. So finally here we set our initial condition, which is equal to 0 in this case. And finally begin with the time loop, which we will iterate over and over. It reinforces the boundary conditions. Remember, all of them are 0 except for U3, which is the U4, which is the top boundary condition of the cavity flow. Okay, so we'll start with talking about the boundary conditions. So here's some matrix manipulation with reshaping, matrix multiplication and reshaping again, and after freeing the memory, lots of functions to free the memory to avoid memory leaks. Here it's computed the boundary conditions for vorticity. Here the derivatives of vorticity, and here finally the time advancement is made through the Euler method. Let's see, it's contained here. Okay, so basically this is the time advancement for vorticity. Here you can see the u and the velocity component in the x direction, the y direction, the vorticity derivatives here, and the Reynolds number for the viscous term, which is contained here with the second derivatives, and here the time discretization. Okay, so let's go back to the main function. So now that we have the vorticity, we can compute the stream function, and here is the step where the Poisson equation is solved. We have to give to the function the vorticity, the discretization in x and y, the max number of iterations for this Poisson solver, and the tolerance, which is the convergence criteria. So let's take a look at the Poisson equation. So basically, this equation right here, let me go back to the Poisson. Here. So this is the Laplacian operator, right? So which consists of second order spatial derivatives. So we have to discretize this using central finite difference scheme. So then we isolate the stream function on the left hand side, and what it's obtained is this. Okay, so this is the equation to be solved and needs to be iterated until a convergence criteria is achieved. On this case, I utilize the absolute error between two iterations. So when the error is less than the tolerance, the convergence criteria, it prints that the Poisson equation was solved with a certain number of iterations and prints the absolute error, and returns finally the u, which in our case it's the stream function. So where was I? Okay, so back to the main function. Now we have the stream function. We can reconstruct the velocity field, computing the derivatives of the stream function. Here there's more memory being freed. Here the velocity field in u and v, x and y direction are reconstructed. We check for the continuity equation to see if everything is okay with our simulation, if the flow is indeed incompressible and the equation is being satisfied. The code then outputs iteration, the time, the progress, the max, the value of the continuity equation fields, and the minimum, which needs to be small. Then there's more memory being freed. Here I will implement in the future some functions to compute the pressure field if one needs to visualize the pressure field. And here is the functions, the call to the functions that print the fields to be visualized by paraview. So here's print VTK. Here's for vorticity, stream function, u velocity, v velocity, and for in the future for the pressure. I can also compute for the velocity, magnitude, and other variables. Okay. And after each time loop, there are some matrices that need to be deallocated in the memory, otherwise we have memory leak, which is pretty bad and can freeze your computer very fast. And finally, when uh, the simulation is over, there's more memory being freed as seen here. Okay, so let's make a quick test. For low Reynolds number, let's put it Reynolds number equal to 100. Here 32 points in each direction. Time step, let's say 0.01, and final time equal to 1. Okay, I think that's good. And for order, we can use a low order scheme since our Reynolds number is small. And I think that's it. I talk about this right here. There is this print VTK function. Basically, it receives the matrix with the field you want to print. And the title, on this case, we will be seeing the stream function. Let me comment this part here. Okay, we'll be seeing the stream function. And basically there's here are the headers of the VTK file, and then it writes to the file the matrix of the field, which in our case will be the stream function. Okay, so I think we're good to go. Right, so let me clear right here. So first of all, let's type make clean. Let me show you quickly my Makefile, in case you're wondering. So in C, you can automate your process of compiling through a Makefile. My compiler is the GCC. Here's the debug flag, the warnings flag, the libs I'm using the math lib, the source directory include, and the binaries which directory will be stored, and the binary file will be named CNavier. Okay, so here's some flags. They includes and make clean. It removes the binaries, the libraries, and the output VTK files. Okay, which will be placed on this folder here. Okay, so let's type make clean so we can now compile the C files. Okay, everything went fine, didn't have any trouble, and now we can run the program. Can run like this and see what happens. Okay, so it's printing a lot of information here. We have to wait a while. I believe it's 60, 70%, 80, 90. Okay, so it was pretty fast simulation. Here we have some information. Poisson equation solved. 0 iterations. This seems weird. Let me check some stuff here. Tolerances, razor tolerance. Make clean, clear, make, and then let's run again. Continuity equation seems okay. It's very low. It means the continuity equation needs to be equal to 0 in the incompressible flow. Let me erase the order here. Perhaps we need a tinier time step. Make clean, clear, make, and let's run again. Okay, now let's see. So now we have, now it looks fine. So it's not always easy to find the optimal parameters of the simulation in order to run smoothly. Okay, now it's ready. So here we see Poisson equation solved with 58 iterations. Absolute error is the order of -7. Continuity equation seems okay. It's a very small number. Okay, so now we can check if the stream function with ParaView. So we open ParaView. Now we go to the output folder, and here we have the output files, which is the stream function. Okay, we change here to surface, and let's go to, we need to rescale, and now can change your colors here. Okay, so I think we need to run this more time in order to flow to be fully developed. So let's close this right here, and then we can increase perhaps 10 time units. Remember that these are dimensionless. And now we make clean, clear, make, and we run again. Now it's going to take some more time since we increase a lot the number of iterations. So all this is uploaded in here in the GitHub. Here's the example video for Reynolds 1000, and here's a snapshot of the video for the vorticity field. This is the vorticity field. You can test you can test this example already, just compiling the C files and running. It's set up to Reynolds 1000. Here we have 64 points in interaction, the time step, and that spatial derivatives are of 6 order. So it should output something similar to this right here. You can change though this time here from 60 to 30. 60 would take a long time since the code doesn't run still doesn't run in parallel, but I'm planning in the future to implement to parallelize the code using MPI, message passing interface. So it should run a lot faster with MPI implemented. So here we are at around 37%. Let's check it already with ParaView. You can check if the simulation is looking good despite not being completed. So okay, So this is what should appear for Reynolds 100. It's a single vortex. Let me rescale. Okay. So this glitch is due to the Poisson equation not being correctly solved. So in order to solve this, we should decrease the tolerance here. So let's press Ctrl C here and then adjust here. So let's take it to, I don't know, -9, and here we can increase to perhaps 0.01. Make clean, clear, make, and then we run. Okay, since I think it's okay. Let's check it out. String function. It seems okay to me. We are around 22% of progress. So it should converge well when it gets to 100. In the meantime, I think I could give you a good overview of the code. Well, in the future, I intend to implement the solution for Taylor green vortices, homogeneous isotropic turbulence, include a scalar like temperature or density for stratified flows. Also implement free surface flows like using a method like VOF, volume of fluid, and case like, for example, dam break and so on. So there's a lot of stuff to implement, and here you're free to contribute as well, to clone, to profit, to do whatever you want to, since this is a GNU license, so you can use this for commercial use, for modification, distribution, for patent use, private use. You can basically do whatever you want. However, you don't have any liability. You have to verify for yourself if this the code is actually, it outputs the physics are reliable, they make sense, they're not trash, they're not gibberish, and of course you don't have any warranty in this license. Okay, so I think it's almost at 100%, and then we can check if the solution converge in ParaView. Okay, so we had a lot of iterations here for the Poisson equation. Okay, let's check ParaView, string function. Okay, so let's okay, I think we've obtained the solution, and then using ParaView, which can if you're using Linux, you can install it like this: sudo apt get install ParaView, or you can go, if you're a Linux user, you can go to paraview.org and download from their website the binaries or the precompile. So here we have Linux, Mac OS, Windows, so it's portable. You can compile this code and run on any machine. Basically, here we have the .ax file of ParaView Linux. We have the tarballs, Mac OS. Here the package file, so you can run this code and visualize the data in any operational system. Okay, so before I end up with this video, I like to show you an interesting tool I use to verify, check for memory leaks, since in C programming language you have to check your pointers, you have to dynamically allocate them and free memory, since it doesn't have a garbage collector like Python and some other high-level languages. But on the other hand, in C you have your applications run much faster than, for example, in Python. So let me show you something here, how I checked for memory leaks in this case, since for the absence in this case of memory leaks. So let's make clean. I change it here to 1 time unit. Clear. Let me find the command here. Where is it? Okay, so there's a lot of make clean. Oh, never mind. I'll just type Valgrind. I need to compile first. So I use a tool called Valgrind. You can install from Linux. Okay, it's already the latest version. So to check for memory leaks, you can use Valgrind. On this case, I check on the binary that was generated. So memory check error. So it's going to run now. It's going to take a while. So I finished running Valgrind on my code, and as you can see here, the summary here. Total heap usage, heap memory, freeze, bytes allocated, and here it's the most important message: all heap blocks were freed, no leaks are possible. So 0 errors from 0 contexts. So this basically means that there are no memory leaks on this code. You can run on your machine free of worries whether or not this code has any memory leaks. Okay, guys, we can also use other tools to check for memory leaks, but I already checked this code with very high matrix here, and using htop, which is a very useful tool in Linux, and there are actually any memory leaks. So hope you guys like this video. Hope you guys find this code useful for learning, for, I don't know, whatever project you're working on, whether you're undergraduate student, whether you are engineer, whether you're a physicist, mathematician, whether you're a graduate researcher. You can use on your research, you can use on whatever you want. You're free to contribute, or you're free to ignore, whatever. So if you guys like this video, don't forget to press the like button, to subscribe to this channel, and share this video. I'll see you next time. Bye.